So welcome to the next topic, the periodic table. We're going to delve a bit deeper into the different groups of the periodic table. These are the learning objectives for the topic. We're going to be describing the change from metallic to non-metallic character across a period, understand how the similarities of reactions in group 1 are related to the concept of this group. Okay. Understand how the difference between the reactions of these elements with air and water provide evidence for reactivity. Then we're going to look at how you can make predictions about further down in the periodic table in the group. Explain trends in terms of group reactivity of both group 1 and 7 in terms of electron configuration. In terms of group 7, know the colors, states and physical properties of at least the first 3 group 7 halogens. Predict the properties of other groups, members of the group 7, and understand about reactivity, looking at particular the displacement reactions of halogens with halides. Before we delve into group 1 and 7, let's look at the periodic table, which was designed by Dmitry Mendeleev 150 years ago today. And this is the picture of the first attempt at the periodic table, basically looking at the different reactions exhibited by the elements. So this is the periodic table, which you're now becoming familiar with. The building block of matter, it's basically the map, which you have to be able to use as a tool as you become more proficient in the subject of chemistry. And today's topic or lesson will be focusing on group 1 and group 7 here, which is in older periodic tables group 17, but this is actually group 7. So in terms of the layout of the periodic table, you can see that groups 1 and 2 are metals. We have this block here in the middle called the transition metals, which we won't look at in too much detail in Shell. In fact, in IGCSE at all. Okay, they're also metals. Group 5 and 3 and 4. Okay, they're now moving into the non-metals. Okay, so group 7 completely is all non-metals. Group 8, of course, being gases, are non-metals. And groups 3, 4, 5, and 6 are combinations of both metals and non-metals. Okay, so in terms of reading the periodic table, in terms of classifying, the elements here are going to be your non-metals. These are the noble gases because they don't react, they're noble because they have the full outer shell. All the yellow, which are these ones here, are your metals. Okay, so most elements tend to be metals. And we have this group here on the interface of the non-metals and metals known as the metalloids, which have basically properties of metals and also properties of non-metals combination. So we're going to start off with group 1, okay, and these metals, which we will discover through the demonstration, will react violently with water. Okay, so groups of elements have similar physical and chemical properties. Okay, so groups of elements have similar reactivity as well. And in terms of group 8, these gases barely react at all because of the electronic configuration. Okay, so why do groups of elements react in the same way? Well, we've already done electron configuration, so you should have a concept around that. Okay, it's because they have the same number of outer electrons. So group 1, being in group 1, has 1 outer electron, which is important in terms of its reactivity. So in terms of this reactivity, basically as you move down group 1, the reactivity will increase, and we're going to explain why using electron configuration later. As you go across the periodic table, the reactivity increases. Okay, and as you go up the non-metals, you're also going to have an increase in reactivity. And we'll look at the electron configuration to try and explain that later. But these are just the general trends. So let's introduce to the group 1 metals. Okay, so the first three we're going to look at are lithium, sodium, and potassium. Now you can see from their density numbers, they're not particularly dense. Okay, 0.5 grams per centimeter cubed, not particularly dense. And they have reasonably low melting points, except, I guess, lithium. But compared to other metals, they have quite low melting points. And you can see the melting points actually go down as you go down the periodic table, okay, down the group. And their densities kind of stay the same. So in terms of the periodic table, we can make, therefore, predictions on the properties of other group 1 metals. So if you look at your periodic table, the element just below potassium in group 1 is rubidium. Okay, so you can look from the physical properties and say, well, I think that rubidium is going to have a lower melting point than potassium. You can see the trend as it goes down. It's going to get lower as you go down. And you're going to say, well, it's probably going to be a soft metal as well, because the first three are soft metals. Now, in terms of reactivity, this is what actually happens. So this is lithium here. We react it with water, and you can see it bubbles, it fizzes. Okay, so that's got a start, a reference point. But when we compare that with sodium, you can see that the addition of sodium, it's a lot more reactive. Okay, now you've got it like swirling around. It's actually melting because it's getting to basically boiling water, so 100 degrees Celsius. And it's giving off this orange-yellow flame. Okay, so it's more reactive than lithium. And then if we look at potassium, you can see a massive explosion. Okay, that bright flame, slightly lilac, but you can't quite see it because it's got kind of a gentle lilac flame. Okay, and you can see it's a lot more reactive than potassium. So again, going back to the idea of making predictions, you should probably think that rubidium is going to be less or more reactive. Okay. Well, it's going to be more reactive because as you go down the group, we'll explain why that is in the next slide. You can see that the reactivity increases. So rubidium should be more reactive than potassium. And you can see also in the table there the observations. You're basically seeing that it's getting more reactive as you go down the group. Okay. So in terms of reactivity and electron configuration, well, group 1 metals are highly reactive. They have to be basically stored under oil because they're going to react with the air and form oxides. Okay, and in fact, rubidium and cesium are so reactive that they have to be stored in sealed glass tubes. So that way, there's no way that air can actually get to them, or oxygen, at least in the air. Okay, so care must be taken not to touch any of these metals with bare fingers, because there would be enough sweat in your skin to give a reaction. Okay, and it's going to form corrosive sodium hydroxide on your skin. Okay. So in terms of group 1, they're all in group 1 because they have a special property in terms of electrons. So if we look, you can see that they have one outer electron. Okay, and in terms of the chemical properties, they all react with water, which we've just seen, to form metal hydroxides. They react with oxygen to form oxides, and they react with halogens to form the corresponding salts like lithium chloride or magnesium bromide. Sorry, not magnesium bromide, potassium bromide. They also form ionic compounds, which we've already looked at when we looked at ionic bonding. Okay, and this chemical property is because they have this one outer electron. That's why they behave similarly, okay, in terms of the chemical properties. Here we go. Because they all have one electron in the shell. Okay. So the explanation for this increasing reactivity is the following. Okay. It increases as you go down the group because the atoms are becoming larger. Okay. The outer electron becomes therefore further away from the nucleus. Okay. Negative electron, positive nucleus. That means that the force of attraction between the positive nucleus, the electrostatic attraction, and the negative electron decreases. There's one negative electron. And the outer electron is therefore lost a lot more easily. So it's easy for the electron to go off and form reactions, okay, form these ionic salts or oxides. So that was the group 1 metals. Okay, so the group 7 elements are called halogens and are diatomic metals. So what do we mean by diatomic? Well, for example, chlorine is Cl2. Okay, it's got basically 2 chlorine atoms make the element of chlorine. And these are the 4 elements you have to be aware of, the 4 halogens. We have fluorine, chlorine, bromine, and iodine. Fluorine's a green color, so is chlorine. Fluorine's a lighter green, I guess. Bromine is a brown liquid, okay? So fluorine and chlorine are gases, bromine's a liquid, and iodine is a purple solid. And you can see that as you go down, the melting point increases, and so does the boiling point. Okay, and we've already looked at the reason for this in covalent bonding. It's because the molecules are getting larger, so the intermolecular forces are getting stronger, so it requires more energy to break them. And there is what they look like. So there's fluorine, there's chlorine, okay, nice green gas, there's bromine, liquid, and there's iodine, which is a solid, which sublimes into a purple gas. So an important way we can see how reactive these elements are is through their reaction with the halide ions. Okay. So what happens is that basically if you react the element with a corresponding ion, so in this case this would be chloride, okay, this one here, okay, because it's made of potassium ions and chloride ions, okay, you can see there's no change. But chlorine, that chlorine gas is formed, okay, and if you react it fluorine with bromide, okay, Br minus, you're going to see a formation of bromine, and so on for potassium iodide. With chlorine, there is no change. With potassium fluoride, with bromine, there is no change with potassium fluoride, and with iodine, there's no change with potassium fluoride. And bromine doesn't react with potassium chloride, and iodine doesn't also react with potassium chloride, and iodine doesn't react with potassium bromide. Okay, so which ones do you think are the most reactive, therefore? Okay, so it's going to be this fluorine is going to be most reactive because obviously it's reacting with the corresponding ions and changing them into the atoms. It's actually taking electrons away, okay, because it's more reactive. And this is an example of oxidation reduction, which we'll look at in more detail next year. So in terms of the reactivity, that's how you can describe it. So basically, as you go down the group, okay, then the reactivity also decreases, okay? So reactivity decreases as you go down the group. So in terms of explaining the trends with electron configuration, here are the three halogen atoms: chlorine, bromine, and iodine. Okay, so when an element in group 7 takes part in a reaction, its atoms' outer shells gain electrons, okay, because it wants to basically, it gains an electron to now become the chloride ion. Okay, and it's known as an anion, of course. The less easily these anions form, the less reactive the halogen is. Okay, so we saw in the previous example that fluorine is really easily able to take an electron from the corresponding ion. Okay. So as you go down group 7, the atoms become larger, the outer shell becomes further from the nucleus, and the force of attraction between the nucleus and the outer shell decreases because the positive nucleus is now further away, so it can't really pull on the outer shell electrons as strongly, which are negative, okay, electrostatic attraction. And because of this, an outer electron is gained less easily. Okay, so as you go down, there's less pull on the outer electrons. So it's basically harder for it to attract the electron from another atom. And that means that the halogen becomes less reactive.
Group 1 of the periodic table is a group of reactive metals. Lithium, sodium and potassium are at the top. These metals are so reactive they have to be stored under oil and need to be handled with care. Lithium is so soft it can be cut with a knife. You can see how shiny the freshly cut surface is. But leave it exposed to the air for a few seconds and it quickly begins to tarnish. It's reacting with the air. This is sodium. It's even easier to cut, and again the shiny surface soon discolours. Potassium is even softer and reacts so quickly it dashes immediately. Another way of comparing reactivity is to place the metals in water. Lithium floats. It reacts immediately, fizzing and skating around on the water, which is evidence that a gas is being produced. By carefully putting a tiny amount into a boiling tube, the gas can be tested with a lit splint. A squeaky pop means it's hydrogen. Universal indicator shows that at the end of the reaction, the solution is alkaline. Lithium reacts with water to form lithium hydroxide and hydrogen. So how does sodium react? Again, it floats on the water and fizzes. The gas produced is hydrogen. And the solution is alkaline. When sodium reacts with water, sodium hydroxide and hydrogen are formed. Sodium is more reactive than lithium. It's below lithium in the periodic table. Potassium is below sodium. So how would you expect potassium to behave? Potassium is definitely more reactive than sodium and lithium. It reacts immediately, and the hydrogen produced ignites on its own. Universal indicator goes blue. Potassium reacts with water to form potassium hydroxide and hydrogen. Rubidium and cesium are elements which lie below potassium in the periodic table. How would you expect rubidium and cesium to react with water? Group 7 of the periodic table is a group of non-metallic elements called the halogens. Iodine, bromine, chlorine and fluorine are very reactive, so they're not found as free elements in nature. Fluorine is a gas, but it occurs in a rock called fluorspar as crystals of calcium fluoride. This is chlorine, a poisonous pale yellow gas. The commonest chlorine compound is sodium chloride, found as rock salt and in seawater. Bromine is a dense, poisonous reddish-brown liquid which easily vaporizes and turns into a gas. Compounds of bromine are less common, but seawater is a source of many of them. Iodine is a solid. It has the appearance of shiny grey crystals. Iodine compounds are also associated with the sea. They're found in seaweed. Fluorine is too dangerous for us to handle. To compare the reactivity of the other halogens, we can see how they each react with the same metal. This is iron wool. For it to react with iodine, it's placed above a few crystals in a boiling tube, in a fume cupboard. Heating the iodine turns it into a vapour. A Bunsen flame gets the reaction going. After several minutes of strong heating, only a small amount of the iron has reacted. It's become coated with reddish-brown iron iodide. Put bromine in the tube instead of iodine, and it immediately vaporizes. Again, the iron wool needs heating, but not as much. This time, there's an easily visible reaction. A mixture of unreacted bromine and brown iron bromide pours out of the tube. Bromine is more reactive than iodine. It's above iodine in the periodic table. Chlorine is above bromine. So how reactive will chlorine be? The apparatus on the left generates a stream of chlorine gas. Concentrated hydrochloric acid is slowly dripped onto potassium permanganate. This time the iron wool needs the slightest lick of a flame before a violent reaction races along. Clouds of pale yellow iron chloride quickly form. Chlorine is very reactive, but which halogen is the most reactive? The halogens also react with aluminium. Chlorine reacts violently with aluminium foil. It's not long before clouds of aluminium chloride leave the tube. Bromine also has a brisk reaction with aluminium foil. Iodine and aluminium powder React once a drop of water has been added.